Okay, brilliant. So I think we'll kick off. So hopefully everything is working for the online Teams people. So yeah, it's a real pleasure to welcome everyone to this VMSG 60th anniversary lecture. So today's topic is volcanoes and climate change. And so these, we don't know VMSG, it stands for Volcanoes and Magma Studies Group. So it's a special interest group and it's part of the Geological Society of London. It's the 60th anniversary, a number of seminars to mark that across the country. So St Andrews has been chosen because of our interest in volcanoes here and particular interest in climate, which is increasingly becoming a big part of what we do. So I couldn't, try to kind of capture both St Andrews and volcanoes with an AI generated image. I'm reasonably impressed. It's gone for the golf course element of St Andrews and a nice big ash-rich with that. So it's done doing an okay job. And I'm delighted to introduce Siwan today. So the VMSG, the organiser, wanted to do a very brief kind of introduction to what we do at St Andrews. So broadly, our group here at St Andrews are really interested in large explosive eruptions. So these are kind of the biggies in terms of volcanic events. They have large, really significant global impacts on kind of human health, the economy, and society at large. And this is made clear, I guess, in 2022 with this huge eruption of Hunga in the Pacific Ocean. So massive volcanic eruption. You can see these weather systems, which are on thousands of kilometer scales. And this is an eruption that is of that magnitude, is a kind of planetary scale process. And really the thing that drives a lot of the work that we do is thinking about how we improve resilience to future eruptions. And from our perspective, what's really, really important is that it really requires a detailed understanding of the kind of source style impact of past volcanic events. And so we as St Andrews look at ice cores, and so for me, ice cores are probably the best record of volcanic eruptions that we have on Earth. They're exquisite because they're incredibly high time resolution. So this, it's not working particularly well, but this is a time series made from ice cores of sulfur over the last few thousand years. And what you can see is that every time there's a really large eruption, it's captured, the fallout of sulfur is captured in polar ice cores, and you get these spikes in sulfur. But the challenge is actually how do we get more out of these records rather than just saying there was an eruption at this time? Because the sulfur concentration alone is telling us very little about where is the source of that volcano? Was it in the Philippines? Was it in Japan? Was it in Africa? And it also tells us very little about whether these were actually climate changing events and actually had a punch to cause even 1 to 2 degrees Celsius in global change. And that's really. And at St Andrews, we're tackling this in a number of ways. Our kind of key goal is to try and figure out this key information, to try to understand something about the plume height of past eruptions, and also trying to understand about the source location. These are the two important kind of parameters that are, I guess, important for understanding the climate impact, but also the volcanic hazard, understanding which regions are the most significant in terms of the volcanic hazard. So what we do are two techniques, so sulfur isotopes and tetrochemistry. The sulfur isotopes to be led and pioneered, let's say, by Andrea Burke, and that is looking at basically sulfur isotopes in the ice core which fingerprint stratospheric eruptions, because you get unique photochemical reactors that impart mass independent fractionation of sulfur. So it's a really novel way of actually working out and obtaining that parameter. What I do and what I'm interested in is looking at the tetra, so pulling out these tiny shards of volcanic ash that make it all the way thousands of kilometers to the ice core and eventually get captured in ice. So that's kind of broadly what we do. So a few kind of insights very, very quickly in just one slide. So what have we found over the last few years looking at ice cores? I think the first thing which I found quite spectacular is that ice cores are a very rich tetra repository. I was expecting to find very little material there. But actually, so this is the eruption of Katla at about 750. This is an ice core sample, and each one of these brown kind of minerals here, I'm not say minerals, but these are actually glass shards. Okay, so these small fragments here are glass shards that have made it all the way to the ice core. And in this subsample alone, there are hundreds to thousands of these shards. So the first thing is that these are rich tephra repositories. For eruptions that are very far away from the ice core, so that previous example was Iceland, but for, say, eruptions that are happening near tropical latitudes, the shards tend to be much smaller. And as a result of that, we had to develop new methods to actually analyze. And so this is some really nice work by Helen Innes, who's here, who developed this new method to look at very, very small shards with 3 micron beams. So it's really pushing the limits of what we can do. And it really was trying to work out the importance of whether you finally polish those shards or not, how significant that is in terms of your accuracy and precision. That is really, really important work that Helen did there. And as part of this study, we've identified new eruptions. Okay, so here's one of the many examples that Volcan Sebaruco, so this is a volcano that blew its top about 1,000 years or so in Mexico. This is what it looks like. And we picked up some of these shards in Greenland ice core. This eruption was known because it blew its top at the time. Some of those shards have been found in North America, some have been found in Ireland. But finding them in Greenland, it not only says, that can just tell us about the dispersal of that tephra, saying that it went almost 7,000 kilometers or so from the source, that allows us, kind of more importantly, to really precisely tell you when the age of that eruption was. So before our work, the age range of this eruption was about 1270 to 910, and that's based on a radiocarbon age, which inevitably comes with fairly large uncertainties. But when you find that tephra in precisely dated annual layers of the ice core, you can get an age that is 941 plus or minus 1 year. So you really can tell exactly when these eruptions happened. And obviously, if you're trying to understand was there climate change at this time, did this have some long-range impacts, knowing the age with that precision is really important. I'm going to hand over now to Siwan. So just a very kind of brief introduction to Siwan. So she is a professor at Swansea University. Joined there in 2004, is that right? And 2012 is when you were made full professor there. So Siwan really works on tephra chronology and the kind of the importance of trying to use these kind of precise, accurate ages of tephra to constrain paleo-environmental proxies. So if you want to understand something about climate change and linking it on a regional scale or a global scale, you need precise, accurate timescales, and tephra and the work that Siwan has done is really, really important. And I was just showing these pictures to Siwan. This is actually, Siwan helped us a lot setting up these methods at Swansea several years ago. And this was literally maybe a week or so before COVID became a thing. And you can see, no idea about social distancing or anything on the horizon at that stage. So yeah, please just give a warm hand, warm applause for Siwan.
Great. Excellent. Thank you very much, Will. Thank you for the welcome and that nice introduction. That's made my life and my job this afternoon much easier by explaining some of the work that we generally do on the ice core. So it's a great pleasure to be here in St Andrews, and it's also great to be part of the VMSG 60th year celebration. So thank you very much to Will and the VMSG for inviting me to be part of this celebration. So this talk, as Will has nicely already outlined, is going to be about volcanic ash or tephra deposits and how we can use and exploit tephra deposits to help us understand changes that have occurred in the past. So this technique of using tephra chronology, I'm sure you will realise we can trace its origin back almost 100 years of using the tetrachronology as a technique and a powerful correlation tool. But what has really changed in recent years is this quest for these cryptotephras, or these microscopic ash deposits, that's really changed the scope of the technique and how we can apply this technique to a whole range of different scientific challenges. So I like to use this title of "A little goes a long way." A little bit of ash certainly does go a long way in terms of geographical distance, but it also goes a long way in terms of the scope of the technique, in terms of what we can now address or try and address and use the tephra in that way. Little did we realise that a little bit of scant sprinkling of ash over past land surfaces would have such an impact on quaternary research. Now, I'm sure you're all familiar with the correlation tool of tetrachronology, but I hope that you will allow me a moment to share with you an animation that just summarises the principles of this technique. And this is nicely illustrated in this animation. Essentially, when a volcano erupts, you have widespread dispersal, instantaneous deposition, preservation, and with instantaneous deposition over land surfaces or ice sheet surfaces, and that's varied then by subsequent snowfall or sedimentation in the marine environment. And in most cases, and I stress in most cases, the geochemical fingerprint of the gas that we can find will be reflective of the geochemical signature of the magma composition, and that usually gives rise to a unique geochemical fingerprint, which of course is really important to provide us with that fingerprinting for tracing these marker horizons over wide geographical areas. That is our tag or our fingerprinting for finding these time parallel marker horizons. Of course, close to the volcano, you have lots of ash deposited, and then as you go further and further away from the volcanic centre, then you see that the ash deposits are much thinner. This is from the lake sediment called from the Faroes, and then an ash deposit preserved within the East Lake record from the Greenland ice sheet. But my work, and many of those in this room, Will, Helen, and those that are working beyond the realms of where we might see the preservation of the macro deposits. And I like to think of the work that I do is essentially this. And those of you in the know, those of you that experience trying to find these tiny glassets, you will know what I mean. We're looking for those tiny, tiny particles. And you can substitute that haystack for any paleoarchive, and this is essentially what we're doing, looking for needles in haystacks. My haystack for the last 2 decades really has been the Greenland ice sheet, and I've been searching for a number of different volcanic ash deposits within that. But you can substitute the haystack for anything, for your lake sediment, for your peat record, marine record, archaeological deposit, and so on. And there are a number of different techniques that have been developed. Either you burn the peat and look to see what's left, or you can actually use density separation, or with the ice you just essentially melt it and then just see what particular material is left. Now, I don't know if you all realise, but this revolution and this fascination with cryptotephras began in Scotland. 35 years ago, the work of Andy Dugmore, he identified the Hecla 4 eruption within a peat deposit from the Cape Ness. And this really did lead to a huge revolution and this fascination, this obsession with the finding of ash deposits in areas far, far removed from the volcanic centres. And you can see some nice illustrations, nice photographs here of the Hecla 4 deposit found in this peat deposit. And then you can see in this paper published in 1989 in the Scottish Geographical magazine, where Andy describes the potential of applying this for archaeology, and that we should now look for all the other known tephras that we know of from Iceland. And in fact, we have found now a number of these tephras beyond Iceland's shores. We found a number of the known eruptions, but we've also found a lot of other eruptions that we didn't know of. Actually, the detail and the new eruptions, previously undocumented eruptions that have been found, is actually quite remarkable. So Andy really kick-started all of this work. Since then, he inspired a number of different researchers, particularly the late Valerie Hall and John Pilcher, who travelled the length and breadth of Ireland, trying to sample almost every peat bog that they could get their hands on. They looked at the top 2 meters and then looked at the volcanic ash deposits preserved for Ireland. And then in the late 1990s, John Lowe and Chris Turney then found the Vedi Ash deposit, which is a mid-Younger Dryas tephra within a late glacial record from Scotland. Again, it all started in Scotland. Scotland was a really important part in the revolution and the quest for cryptotephras. And then Chris Turney and John Lowe also then inspired people like Stefan Vastergaard to look in Sweden and in Scotland, and then also even finding the Vedi Ash in Russia. My involvement in cryptotephras started in the late 1990s. I did my PhD with Chris Turney and John Lowe, which really was an exciting time to start working. We didn't really know what we were going to find, and it really was a PhD project. I wish I could go back to that time just to start that again. It really was the crest of the wave in terms of finding the different tephras within late glacial sequences across northwest Europe. The rest, of course, is history. And by now, as Will illustrated, there are a number of ash clouds that we can extend their fingerprint of thousands and thousands of kilometres beyond the volcanic source. So we have an example of the White River Ash. Valerie Hall and John Pilcher actually identified this tephra back in the 1990s in Irish Peaks. They didn't know what it was, and it was 20 years before they realised that actually this related to an ash deposit and an eruption in Alaska. From the Bonner Churchill Massif, and then there are a number of other examples that I could refer to as well. CIS being found in Icelandic tephra, being found in Romania, Azores tephra in Svalbard, Lake Malawi, Toba tephra in Lake Malawi. So basically and essentially the work that we do is in areas far removed from the volcanic source. And I have to say, I feel like a bit of an imposter here presenting to the VMSG seminar, when in fact I actually don't go anywhere near a volcano in terms of the work that I do. I work in very distal areas, trying to find these needles in haystacks. So, tephrochronology and the finding of these cryptotephras and these microscopic deposits has been now applied in a lot of different settings and a lot of different priorities from chronological problems, trying to use these tephras for fixed points or testing various age models. A lot of my work has been to try and use it to address and look at abrupt climate changes and using these fixed points to look at whether there are phasing and leads and lags between, say, the oceans and the atmosphere. A lot of work, like Will mentioned, on the societal resilience, landscape development here in St Andrews, looking at vegetation succession and looking at the processes and using these tephras as markers. And then, of course, there are a number of different applications in terms of providing new ashfall frequencies, contributing to hazard assessments, and then the biggie at the moment, I think, is that looking at volcano climate interactions. And these cryptotephras can really address and help us understand the impact of various volcanic eruptions on climate in the past. So that gives you a little bit of potted history to start us off in terms of how we've got to this point. And for the rest of the talk, I want to share with you the work that I've been doing on the Greenland ice sheet. So as Will was already mentioned, the Greenland ice sheet and the polar ice cores provide us with some really invaluable repositories and archive of climate history. Here are some pictures of the work that I've been doing as part of the East Grip project. I've been fortunate to be part of 2 different ice core drilling campaigns, one in Nîmes and one in East Grip. At the time when I was a part of the East Grip work, a lot of the processing was done on site. There was some initial chemical work done. You can see in one of the top pictures of the processing work there done underneath the ice surface, and the processing line there with some initial electrical conductivity measurements and DEP measurements, and then eventually cutting the ice into various pieces and packing the ice to allow us to return the ice and samples to Europe. So the ice cores, tephras are a wonderful thing, but the ice cores are also wonderful things. Because we have the ice sheets and snowfall falling annually on the ice surface, we have this beautifully preserved, annually resolved record that in Greenland allows us to go back around 130,000 years. And in the early days of ice core exploration, they really were ahead of the game. They really knew the potential of using ice core records to look at the past volcanic history. And the great thing about ice cores is that it preserves the soluble component, preserves the aerosols from the volcanic eruption, as well as the insoluble particles, the tetrad component, all preserved within the ice core record, or preserved together. So it does provide us with an ideal opportunity to look at volcanic history and to reconstruct volcanic history in the past. So the initial work on the tetrad record and the volcanism in the record was focused on acidity peaks, and they did this by looking at the electrical conductivity measurements of the ice, a very simple technique where they dragged two electrodes across the ice surface, and the current and the voltage difference between the ice, when that was high, it indicated high acidity. And so with this count from the top principle, where you have these annual layers within the ice, what they did then, they had very good control on the ages, and then assigned well-known historical eruptions to some of these acidity spikes. And that middle figure there shows some of those well-known eruptions linked to some large acidity spikes, like the Eltiau, the Tambora eruption, the Katmai eruption, and so on. So this is where they started developing a volcanic repository record from the acidity records. After that, there was some targeted work looking at some macroscopic tetrad deposits. There weren't many in some of the early records retrieved from Greenland. This tended to focus on the summit cores drilled back in the early 1990s, the Grip record and the GIST2 records. There were around 3 or 4 macro deposits, just like that photo illustrates there, that they identified. So they focused on those, but they also then used those acidity peaks to look for well-known historical eruptions. And a number of volcanic eruptions were found, tetrad deposits from those volcanic eruptions were found. Listed here, we've got the Eroshiökel, Vati, and so on, were found. To notice that some of those have got, the text has been, there's strike through some of those. And essentially, some of this early work that was undertaken was really quite difficult in terms of getting robust geochemical data and robust geochemical fingerprints. They did a lot of automated SEM analysis, where they would analyze every particle that they could find and that was left within an SEM stub. Some of those particles are shown there. Some of them were really, really small particles. And they did manage to get some geochemical records from them, but some of the comparisons that they did between some of the proximal deposits and some of the signals from Greenland were incorrect. And I think subsequent work and subsequent return and looking at some of that geochemical data demonstrate that actually some of these tetrads don't relate to, say, for example, Marks and Helens or Chichon. So this early work in the late 80s and early 90s was always linked to the ice coring campaigns at the time. So towards the end of the 93, I think they completed the summit cores retrieval. And then after that, there always seemed to be a bit of a lull in terms of the tetrad excavation within the ice core records. They weren't as quick as, say, the work that was undertaken in the terrestrial realm to capitalise and keep the momentum going in terms of finding some of these microscopic deposits. So there really was a bit of a lull towards the end of the 90s and early 2000s. My work started in the early 2000s, and that was linked to the North Crib record. During my PhD at Royal Holloway, Sigfus Jonsson, the late Sigfus Jonsson, who visited us at the time, he visited Royal Holloway. He brought a crate of Carlsberg beer under one arm, and then a crate of these filters, a cardboard box of filters that they had collected during the ice coring at North Crib. And what they did was set up a filtration system on the ice sheet. And when they were doing some chemical analysis, they fed the wastewater through a filtration system and collected all the particular material. Now, in theory, that should really give us a good insight into any volcanic particles that was preserved within the ice, but it was actually really, really difficult work. Those particles, if anybody's worked with these kind of nuclear pore filters, they're really quite mobile, they're really difficult to manipulate the particles and to get the particles off. I spent a lot of time trying to move things using a steady hand, keeping off the caffeine, and trying to move the particles from those filters onto stubs or slides in order to prepare them for geochemistry. And all in all, this approach really didn't work, but that was my first introduction to try and find some of the microscopic particles. And after that, we realised, no, we actually really need to have a dedicated piece. We really don't want to have any wastewater. We want to have a dedicated piece of the ice core in order to look for any microscopic particles that may be present. And so that's what we did, and we returned and spent a lot of time in the freezers in Copenhagen, where they archive the ice cores from Greenland, and we spent a lot of time cutting a very small sliver of ice from the side of the ice cores, and then essentially we looked at meters, thousands of meters of ice from the Greenland ice sheet. You can see the very small sliver of ice that we have. Those were then packed into bottles. For us, it wasn't important that we have transporting them as ice. For us, it's fine for us to melt the ice and then transport the samples as water. And it's very, very simple. You just have to remove that water by centrifugation and look to see what's left. So in the early days, we started working and looking at the samples on slides like these ones. We have thousands of these slides in which all the samples should be embedded within the squares, within the middle of those slides. And then we spent ages looking at light microscopy. Yeah, this is the kind of fields of view looking, as Will already illustrated, just looking for these tiny particles within a background of dust and other particles, fibres from glove fibres and so on. So we spent a lot of time looking for these needles in the haystacks, and the main thing for us was to really use the tephras as a way of correlating records between different archives. So we wanted to find tephras that could be found uncommon to the ice core records as well as the marine records. Now, in terms of what we found, this figure here shows the time along the axis here, and then we know age, and then the grey curve here represents the oxygen isotopes for North Cape, and those abrupt climate changes that characterise the last glacial period. The red lines represent each volcanic deposit that was found during the summit campaign back in the mid-1990s. It's focused on those macroscopic deposits as well as those targeted, well-known historical eruptions. So that was the situation at the time. Our work, we sampled, as you saw in those animations, a number of meters and meters of ice. And the green shading here just represents what we have sampled. And so the tephra record from Greenland now looks like this, where there are a number of new ash deposits identified. This now is a catalogue of volcanic events, and because we have the ice cores are annually resolved, then we can provide ice core ages and independent ice core ages for each of these deposits. Now, I don't think we were expecting to find as much, but this does give us new insights into eruptive frequency in the past. As you'd expect, being so close to Greenland, we have a lot of eruptions preserved from Iceland, a lot from Grimsvötn, from Katla and Kverkvoll. Most of these are previously unknown volcanic events, and because we don't have a very detailed record, pre-Holocene record from Iceland, then this distal record provides us with new insight into eruptive frequency and ashfall history in Iceland during the last glacial period. So this is a way of using the distal record to fill gaps in the volcanic history. So for each of these deposits, just to give you a flavour of the type of data sets and the records that we are producing, this is the latest instalment for the last glacial interglacial transition. So this is from 18,000 years to the Holocene. And Eliza Cook, who has spent a lot of time working on this time interval, she looked at the three main deep ice cores from Greenland, North Cape, and Neem, and has identified a range of different, sorry, if you pointing at the screen, a range of different tephra deposits within North Cape, within Grip, and also within Neem. For each of these, Then she has given age estimates, geochemical signatures based on major elements. Most of these, as you see, are basaltic, but there are some rhyolitic. And then she has spent a lot of time collecting trace element data as well. And this is one thing that we see, particularly for the basaltic eruptions, which is very, very important, to give us an initial diagnostic fingerprint. Many of the basaltic tefras have very similar geochemical signature, and if we want to find the unique geochemical fingerprints for correlating across wide geographical areas, then we really have to have a diagnostic fingerprint. And the trace element is an added element that, if it can be applied, can be quite useful to ensure that we are linking and using the tefras and correlating the right tefras to different archives. So Liza found a number of tefras, mainly from Iceland. She found a couple from the Pacific Arc, and I'll come back to talking about those Pacific Arc tefras later on. Those of you who are interested in this period, you may be familiar with the Lacazette eruption in the Eifel volcanic region. This is one tefra that we have looked at. In fact, I started looking for this one during my PhD. Still elusive within Greenland, but also still elusive in most of, well, in northern Europe. It's been found in Sweden, but there is no Lacazette preserved as yet. But we have exhaustively looked for it within the icicle deposits. So based on that, there are a number of volcanic ash deposits that we can look for. And what Eliza has done is then try to pull out which ones are most valuable to us in terms of using them as fixed points or correlation, precise correlation horizons. And she is trying to identify a number and pulled out the ones that are most valuable based on their stratigraphic positions, based on the fact that they should be close to abrupt climatic transitions, in order for us to try and test the leads and lags between different regions, whether or not they are widespread. So if they're found in 3 different icicles, then it's clearly they're likely to be more widely distributed and could be found in other records, or indeed when they have distinct geochemical signatures. Eliza in her work has identified 6 that could be correlated to the marine record. This is actually quite challenging work to identify primary deposits between the ice and those in the marine records, but she believes that there are 6 correlations highlighted in orange here that can be correlated between the marine and terrestrial record. One group has been successful in trying to link together the marine and the icicle record. This is the Bergen group. What they've done in terms of looking at phases and using some of these tefras to compare the climate development and looking at changes in the oceans and also within the atmospheric realm. This is done by the Bergen group. This was published in a few years ago. What they've done is tune their records based on magnetic properties and sea surface temperatures to the North Rig, and then it used some of those basaltic tefras that we found in Greenland and also found in the Nordic Sea in this record just here. They then used those as markers to assess whether or not that tuning was indeed correct. And they've used that to suggest that these transitions, these abrupt climate transitions, or these Dutch Gershka events, are indeed occurring synchronously. But they also make some initial hints within their papers that actually, if you look at some of these events, that there are some initial changes that are occurring within the ocean. So this lower figure here, I don't have time to go into this in detail, although they're saying the main transitions are occurring synchronously, there is some hint there that they suggest that there are some initial changes occurring within the ocean. So that's just an illustration of how these tefras can be used to look at some of these abrupt climate events during the last glacial period. In addition to that, I mentioned that these were previously a non-volcanic event. We can also delve into this record and look at the eruptive frequency. Some of the work that Anna Bourne has been doing has allowed us to look at the changes in productivity of the different Icelandic sources. So during the last glacial period in the between 50 and around 35,000 years ago, Grimsvötn was a particularly productive system, and that seems to then quieten off. And in the latter period of this phase, what we're seeing is that other sources like Katla and Kverkjon seems to become more productive later on. And we're also trying to look at the ashfall frequency in terms of how this relates to things like ice-rafted Heinrich events, and whether or not possibly that some of these events may be related, and this increase in recurrence rate is linked to any ice loading on Iceland. So there are a number of different applications and significance to the different records that we're finding. In amongst the dominance of Icelandic projects that we're finding in Greenland, we are also finding a number of tethers that originate from the Pacific Arc. One of those is the Tawada, which is from Japan, around 16,000 years ago. You can see in this figure the suggested trajectories of dispersal to Greenland. There are another 12 Pacific Arc tethers also found during the last glacial period. And this recurrent ash dispersal to Greenland from the Pacific Arc is something that we also see during the Holocene. This is illustrated in this map here, that really demonstrates that Greenland is this linchpin, this very valuable archive that seems to be where a number of different ash clouds are converging. And on this particular interval in the middle Holocene, what we are seeing is that we can pick up ash from 5 different volcanic sources, 4 of those from the Pacific Arc, and indeed the Hecla 4 that was originally found by Andy Dinkmore in Scotland 35 years ago. So this particular, what we're thinking is the Greenland ice really is that important repository. There are, of course, a number of ash clouds I could add onto this, with Will's discovery of the Mexican tephra in Greenland. There's also work by Victoria Smith finding tephras from El Salvador, also in Greenland ice. So there are a number of ash clouds that now converge on Greenland. One of the tethers that we found, Mashu, which is found in Greenland, this was thought to be a very local eruption, very small eruption where ash was deposited very close to the volcanic centre. We're finding a huge amount of ash from this eruption in Greenland. That's just some image here. And the particle sizes are quite extraordinary here. We've got some that are very small, from 3 micron all the way up to 120 micron. And there are thousands of glass particles transported and deposited in Greenland. Now, I like looking on the Pacific Arc tethras because different to Iceland, they have some very distinct geochemical signatures that allow us to really demonstrate and pull them apart. This just shows the major element plots. We've got the Mazama, the KS2 eruption, and then the very low potassium Mashu products. And this is also reflected in the trace element signatures that clearly show that these are very, very different to the Icelandic rhyolites. And by finding some of these well-known eruptions during the Holocene period, 3 of these are large caldera-forming eruptions. Finding them in the ice cores allows us then to provide independent ice core age estimates to each of these events. And in some instances, we can then address and resolve some of those divergent age estimates for different eruptions. So, for example, Hecla 4, this was originally dated to about 4,200 years before present. Our ice core age, which is shown in the blue bar here, provides a very, very tightly constrained age estimate. It shows that the age is proposed by Andy back in the mid-1990s, probably too young, but it does overlap with some of the work that John Pilcher did on the Irish peats and also the VAV records from Germany and Sweden, but it does diverge from a new VAV record from this year in southern England. And that may be based on the way that the Disney record is putting together VAV records as well as a Bayesian analysis and carbon-14 record. But our record, our ice core age for Hecla 4 is more precise and allows us to address some of the diverging age estimates. The same applies for the KS2. There's a big disagreement with this large caldera-forming eruption. Radiocarbon age estimates from proximal settings suggested that it was quite young, shown here, whereas more distal occurrences and dates from Newfoundland demonstrated that it was much older, and that is indeed what we're showing with the ice core ages as well. So that just shows that some of the ages from the proximal deposits from Kamchatka are actually too young. And we can go on, there are a number then, we can provide new, more precise dates for the Mashu eruption and also for the Mazama. So finding them in the ice core record really is very useful for us indeed. So one other application of the Tephra record in Greenland, I won't go into this in detail, but this really is the pioneering work done in St Andrews, where the Tephra records can not just be used as a correlation tool, but providing constraints on the volcanic forcing data set. So shown there is the volcanic forcing data set, the latest provided by Michael Siegel, showing this is based on the sulfate aerosols from the ice core records. And of course, until you have those tephras in association with those sulfate spikes, then most of the eruptions and their latitudes are going to be quite speculative based on the approach of using the sulfate aerosols to developing and forcing data sets. But there are more and more results that are likely to be published in the next few years, which will add new constraints to this volcanic forcing data set. So I will finish off. These are just some of the applications. I am going to finish off by just sharing with you some new work that I'm planning on doing over the next few years, and that is linked by turning south and looking at the Antarctic records. Now, you may be aware that there is a new project or new momentum to try and find the oldest ice from Antarctica, and this is where I think that the Tephra records that are preserved within the ice may contribute a little bit. It will be tough work, it may contribute to the work to find the oldest ice. There are three major projects working in a collaborative competition. They're trying to find the oldest ice that is older than 1 million years, trying to go back over the mid-Pleistocene transition in Antarctica. So there's the European project, the Beyond Epica project, the Coldex project, which is looking at the margins of the Antarctic ice sheet where there might be ancient ice that's being brought up to the surface and looking for the oldest deposits there. And then the Australian Antarctic program are also calling in a close location to the Beyond Epica project. So it's a major challenge to date the ice. This record of between about 750,000 years to 1.5 million ice is likely to be incredibly compressed. And there are some exciting developments using trace amounts of iron 40 to constrain the age of the ice. But they have very large errors, and the tuning to the marine records is the only really approach that they can do. But that then precludes then phasing estimates and assessments of phasing. And so I think that there might be a little bit of hope of trying to find some tephras within this oldest ice in order to provide some age constraints. And in particular, there is one tephra, one big eruption that's preserved in the marine records in the Ross Sea that is argon dated, so it has its own absolute date. And I think finding that within some of this oldest ice will provide a marker. But of course, just finding it will be that needle in a haystack, especially when the record is so compressed and the resolution is low. So that's where my attention is turning at the moment, is to work on the Antarctic ice, and hopefully in the future by drilling into what they are doing, by drilling and trying to retrieve the oldest ice. What they are finding is that they're bringing a lot of much younger ice as well, and there's a lot of ice available that we can look at other intervals and then addressing a number of different questions on some of the younger ice as well. I will leave it there. I think I'm running out of time. So thank you very much for your attention. I hope that you've seen the different applications of how tephras can be used to understand different questions related to the past.
Yes, gave us a clue of some of the different topics. Has anyone got any questions? Yeah, Andrew.
Siwan, thank you so much for a great talk. That was fantastic. And thanks for all of the support you've given to our group here. It's been really fantastic. You also alluded to that, but I just wanted to reiterate that. My question for you is about the radiocarbon. I found it quite interesting that the ice age, in both of your examples, n=2, granted, the ice age is older. Like there seems to be like occasionally you get this like positive radiocarbon bias or young bias in some of the radiocarbon dates. And and I'm assuming those have all been recalibrated. So is that just that when you're measuring, trying to get a radiocarbon date of a tephra, you're measuring something above the tephra, and there you just don't have a good constraint about between when it was deposited and.
They tend, so the typical range is based on the number of different radiocarbonation, the number of different heat logs above and below where they found the tephra. That's been recalibrated. So when you see the probability distribution plots, that's been recalibrated because they provided one age. For the pilcher age, they provided this wiggle matching approach, and we've just used the age of that wiggle matching. We haven't recalibrated that or remodeled. So yeah, it's interesting. The Kamchatka example, the KS2, there's something odd. There's some of the ages are often very young for the Kamchatka tephras. So that you can see that KS2 clearly there's a big discrepancy between the ages from the proximal deposits compared to more distal, like Victor Jensen's work from Thin Ice Pond is a late sediment record.
Right.
So
and it's usually, is it organic matter that they're?
Yes,
it's organic.
Yes. Yeah.
Interesting. Thanks.
James.
Thanks, Jen. You talked about the wonderful things you can do with the data and geochemical fingerprinting of the tephras. I wonder if you could talk a wee bit about what has been done on what you might be able to say from kind of the amount of tephra for a given event. You kind of alluded to this with amounts coming from different places, but that's still kind of a fingerprinting of different places. Can you say anything about nature of explosivity or eruption size from something about the number of tephra shards or the nature of the tephra shards in a kind of analogous way to people who use the sulfur concentration tubes?
I don't think we can from the concentrations. I think to go down that route, we probably need to do a bit more work on shape and then do a bit of modelling to incorporate the ice core occurrences with other occurrences. I think just looking at what we've got in the ice would just be a step too far, because there are so many different factors in play, and I think sometimes, we're finding into some ice cores but not in others, and they should be there. So I think the depositional factors that affect the tephra might be a step too far there. But I think there's definitely a lot more work to be done on looking at size and the shape of the particles and what that might say about the eruptive processes in the grander context by bringing in other occurrences as well.
Yeah. Oh.
This is probably a very naive question, but with all of these, this sort of seems to be huge, ever expanding, exponentially expanding database of tephra compositions. Is there kind of a global database, sort of like that anyone can access to see?
So there are various databases. I think you could look just in terms of volcanic events. Estonia does incorporate some in terms of the occurrences of these and the timing of some of these events. Then there's the tephra base, which is an Edinburgh-led project that tends to have the Icelandic deposits, and then there might be, depending on who submitted data to it. And then the big, the LAMIV data set. So there are a number of different databases, but nobody's put it together in a global context. I think that would be a huge amount of work. But there are different pockets of information where you can obtain this. But in terms of the green and ice cores, they're all in different papers. Yeah.
Yeah,
probably worth
whenever you meet technologists, they always say you should do a database. Yeah, it would be good.
And I think that we know so much more now by looking in these distant areas. Far more than we ever anticipated in terms of unknown events. Lots in the Holocene even that we are originating from Iceland. In distal areas but not present in Iceland, so there's always new data that's being generated.
Yeah, great.
Yeah, just to follow up, really, you kind of alluded to kind of depositional processes there. just wonder here, you kind of present these as though, are they occurring in discrete layers, or is there some sort of smoothing or migration? Or?
No, they are in discrete layers, and actually the work that we've done in the last glacial period, we're looking at, because we were trying to cover so much time, we were actually looking at samples that covers, in terms of, it was 20 centimetre samples and 15 centimetre samples throughout that glacial period, and that covers a different range of time. And then we would look at, say, the sulfate records. I think a lot of the work that Will is doing, because they're looking at more recent time intervals, then you're looking at early changes, and you're able to look at some annual positions, but they are very tightly constrained in most cases, yeah, so there's no steering at all, really. But in your glacial period, we're looking at slightly wider, so you wouldn't expect to see that steering.
Yeah, hi. Yeah, thanks. It was quite an interesting talk, but I'd like to ask you a bit about this geochemical fingerprinting. Actually, I have two questions at this point. My memory of what people were doing with the Yellowstone events in terms of trying to fingerprint those as you went across Western North America was that there was a very severe chemical differentiation from source as you went along in the plume distance. And that differentiation was not always constant in terms of the major elements or the trace elements. So has it moved beyond that now to where you can, with confidence, even though you know this happens in the plume cloud?
I don't know much about Yellowstone, but I think the work, because there's a lot more work done in proximal areas, looking at how the deposit has changed. So if you get a fallout deposit where you can see this evolution, I think comparing that to some of these distal occurrences allows us to work out whether we've got part of the eruption or whether we're looking at full eruption and distal areas. I think that really has come on in terms of how we're linking the proximal and the distal records together.
Okay.
But there's still a lot to be done. Some of the geochemistry can be quite difficult sometimes. And often we can say, okay, this is probably likely to be Iceland. Some of the Pacific architectures clearly are very different. And we know, and we're very confident.
Yeah.
So there's some that we're more confident than others. But I think bringing together those proximal records with the distal records, and we might only have a small snapshot in the distal records.
Okay. Okay. The second one, I think I heard you say something about ice loading or unloading on Iceland. And is that something that people have thought about? Because when you showed your barcode distribution of volcanic eruption concentrations, and there seemed to be this, not a periodicity, but a pattern in it. Is that linked to some sort of loading, unloading process?
So a lot of the work in terms of looking at how ice unloading has affected volcanism has been done during the last deglaciation period. But the figure I showed was between 50 and 25,000 years, and that's the only period where we sampled all the ice flows continuously. So we wanted to have somewhere so there was no changes in any kind of artifact of sampling on where we sampled. That ice loading and unloading then is just linked to those abrupt climate changes during the last glacial period.
Yeah, but you were showing sort of numbers of ash, and there was this increase and then decrease, and I don't know if that's magma chamber influx and eruption. No, sorry, not that one. You had this one, yeah. So that, when you look at it, the red stuff, those you're in. So not anything like magma chamber, build up and expulsion and or ice loading or unloading, because those are 100,000. What are those? 10,000 year? Yeah, 10,000 year. Okay, no, okay, I was just curiosity.
Yeah, and I think the work that we have done, we're still a little bit unsure of what that actually means in terms of the eruptions and whether or not there is a response during these TO events. There just seemed to be a slight increase just before one of these abrupt climate warmings. So maybe there's something to do. I think most of that work has been done in the deglaciation.
Yeah, I think sort of the proximal stuff in Iceland in this case, maybe in the sulfur record there's some hints of increasing, but certainly like Antarctica, which is very far away from any major volcanoes. There's no obvious place to place some material there. Yeah, not entirely convinced. Were there any other questions? Yeah, sure. Is there any other questions in here? Check. Not very good at doing 2 meetings at once. I guess maybe a quick question here. I guess to talk about how do you incorporate trace elements? You know, do you think that it is going to be possible to do that for all of these eruptions?
At the moment, only where the grain sizes permit. Using laser ablation, I think that is. Yeah, we managed to do it with some of the Pacific architectures.
Yeah.
But it just provides us additional diagnostic fingerprints to be more confident. But to do it across.
Have you pushed it to anything really? What are the kind of smallest
I think
shards?
I would say Paul Albert is the expert on trace
Yeah.
elements, and I would say that it would be about 15 microns.
Okay.
And let's be pushing it. Yeah.
Great. Cool. Is there any final questions for anyone here? Yeah, Julie, you've got a kind of tentative.
Why not?
Yeah.
I was fascinated by the fact that you saw an eruption in Japan making it to Greenland, you know, going across all the various atmospheric circulation cells. Is there any sense that some of these small particles are magnetic and therefore you're following magnetic lineation or magnetic line, you know, field force?
I don't think they would be. I think, no, the iron content is quite low, so I don't think they would be.
And this is a normal trajectory to go from whatever that was.
Yeah. Do you know what? Ida Ponomareva, who has been working in the Kamchatka area, she came to Swansea in 2013, and she really wanted us to look for some of these tephras from the Pacific Arc in Greenland because they had such an issue with trying to date some of these eruptions. She was amazed. She came in 2013, and now suddenly we're finding a huge number of these in both the last glacial and also in the Holocene periods. So there just seems to be this recurrent pattern. I don't think they might be electromagnetic.
Well, not you know, not like magnetites, but you can get piezoelectric characters and even quartz and feldspars, right?
Okay.
So, yeah.
I think there's a lot more we could find as well. So,
Great. Okay, I think that's probably us out of time. So can everyone just thank coffee downstairs in the fortune, so please feel free to hang around and have tea and coffee. If you want to have an informal chat with Stuart, then please do. Thank you again.
We're all in this room. Form. We're all together.
You're in it together.
The people who are, I'm fine in this room. Yeah.